All right, I'm going to go ahead and share my screen and pull up the review. So this review is broken down by chapter. I wanted to make sure that hang on, that's not what I'm doing. There we go. I wanted to make sure that we covered all of the chapters that you guys are learning, okay? So chapter 1, which I think some professors choose to omit, so depending on your section, you might not be learning chapter 1. I think it's still important background to learn, just so, so we're just gonna go through a couple of short questions about it. So the first question is rank the weak chemical forces by relative strength, okay? So the way that I like to approach these problems is, first of all, what's the weakest force on this list? Hydrophobic, ionic, hydrogen, or van der Waals? Van der Waals, yeah, you're exactly right. And that's actually why this one is B. So I kind of made this one a little bit too easy, just because I wanted to make sure we were all on the same page with it. The way that I like to solve these problems in general is, I know that I'm sorry, I don't remember who said it, but like what was said, the van der Waals forces are the weakest. Then we know that hydrogen bonding is stronger than van der Waals bonding. The reason that I didn't put too many trick questions here is because those do vary. So you can have an ionic bond that's stronger than a hydrogen bond and vice versa. So I want this one to just be like a make sure you know that the forces exist kind of question, okay? All right, moving on to number 2. So based on van der Waals energy profile, which is the graph below, which I'm going to pull up in a second, which of the following is false? So I'm going to go ahead and zoom out just a little bit so we can see that. Okay, there we go. All right, so a little more. Okay. So, and I want to use this more to go through what the van der Waals energy profile is telling us rather than the details of this question itself. So, looking through this profile, on our y-axis we have energy. Where's my mouse? There it is. On our y-axis we have energy, and our x is distance. Okay. So when we're thinking about distance, this I need to zoom in. I need to scroll just a little bit. Okay. So letter A says this line will never cross the y-axis. This has to be true because if this is representing the distance between the radii, then the first element is over here. The second element is over here. They each have their orbitals and electrons and stuff. So the bond that forms between them can never overlap the two atoms. So it can never cross the x-axis, which makes this one true. Okay, does that make sense to everyone? Or does anyone have any questions? Feel free to type them. B, the energy tends towards 0 as the distance increases because the atoms are too far away to bond. Okay, so that's a really wordy one. So I'm just going to go piece by piece. The energy tends towards 0, okay, as distance increases. So I'm looking at my x-axis because x is distance. So as it increases, yeah, we're tending toward this 0 line. Okay, and why is that? I gave the answer away up. Yes, it is because the atoms are too far away to bond. But what does that mean? When we think about these ionic interactions, they always come down to Coulomb's law. When we think about the hydrophobic interactions, they always come down to distance. Pretty much everything is affected by the distance between the two atoms. So if the atoms are right next to each other, they affect each other more strongly than if they were really far away. And that's why when they get really far away, that energy is about 0. Okay? Okay, there we go. All right, and then C and D are together. The negative energy is a bond being broken. So I want us to think about, here we go. Sorry, I'm still getting used to OneNote, I apologize. So I want us to think about this from the perspective of what's happening. The positive energy is the bond being formed. So everything above this point right here is the bond, okay? So now as soon as we cross into this negative, there's no bond because there's 0 energy between them, right? Well, not really. This 0 energy is being released in order to break the bond. Then as they get further away, they stop affecting each other. Is there anything on the screen? I am drawing on OneNote. I'm not sure if you can't see. I'm going to stop sharing and try it again, okay? Sorry about that. Share. Okay. Please let me know if you can see that. I guess I should ask, can anyone else, or is anyone else seeing that black screen? Okay. All right, fantastic. All right, okay. So, like I was saying before, I've got to find my mouse again, I'm sorry. Okay, there you go. This point right here isn't saying no bond. It's really saying the bond is about to start breaking, it's losing energy. And then as soon as we cross, okay, I don't know what I just did. As soon as we cross this point right here, that's when the bond is broken and they stop affecting each other. All right, and likewise, the positive being the bond being formed, once we cross this threshold again and go above it, that's them affecting each other positively. So these two, this point right here that I labeled, and this point down at the bottom that I labeled, these two have names. So this is the point of highest energy, okay? No matter what happens with these two atoms, they cannot get closer together, and so they can't get higher in energy than they are now, okay? And this down here, sorry, still trying to find, there it is, okay. This right here is the point of minimal contact. Minimal contact. Because any further away and they stop affecting each other, okay? And that's why E is wrong, because a bond can't form when the atoms are significantly far apart, simply because, I mean, they can't affect each other, okay? Does that make sense to everyone? Are you guys okay with the reading of this graph? I know it's not the most intuitive thing in the world. Okay, I don't hear any dinging, so I'm going to take that as a plus. All right. If you guys have any questions, feel free to ask them at any time. Like I'm trying to use the review more as a general rubric for the things we need to cover, more so than, you know, we need to cover only this stuff. Okay, so number 3 for chapter 1, what are the most abundant atoms in the human body in order of most abundant? So this is one of those memorization-based questions, and there are very few of them on this review. I just wanted to make sure that that you guys know that these things can appear on exams. These things are, you know, common questions to be asked, and so I wanted to bring them up. So the way that are you going to share the questions after this session? So these sessions are being recorded, you guys can see. They'll be uploaded to YouTube shortly. I don't know exactly when. I'm not sure how long it takes. And then you guys can check it on there, okay? Okay, so like I was saying, so this question is more to remind you this can be asked, and it has been asked in the past. The way that I like to remember this one, and I'm actually just going to go ahead and show this now, is we're 70% water, okay? If we're 70% water, that means most of us is H2O. And in water, hydrogen is more abundant than oxygen. So that's why, gosh, sorry, I keep losing my mouse. There it is. Hydrogen is more abundant than oxygen. Then between carbon and nitrogen, most of our structures, as you guys probably learned with how like significantly find organic chemistry, carbon is much more prevalent than nitrogen, okay? And so the answer to this one is B. There it is, B, okay, all right. And last question for chapter 1, what is the general form of an amino acid? Again, I don't like these memorization questions. This is more to remind you, amino acids are on your next exam. Totally fair game. You're expected to know them, structures, 3-letter codes and 1-letter codes. But yeah, so the general form of an amino acid, actually, I'm gonna make this into a poll for you guys, because I think you might. Amino acid form, A, B, C, and D. Okay, and if you guys want to go ahead and vote in the poll, I want to make sure you guys remember the structure. Okay, we got 2 for C, 3 for C, 4. Okay, I'm just going to assume most of you guys think it's C, and go ahead and stop the poll. And you're absolutely right. So it is an amino group. Let me see, central carbon, you've got a hydrogen, your variable R group, an NH2, which is an amine group, and a COOH, which is your carboxylic acid. Right, very good. All right, so that is as much as I gave you guys for chapter 1. It's a fairly short chapter. chapter, and a lot of it is conceptual based. I just wanted to touch on a couple of the key points. So chapter 2, we're going to go ahead and start. This is one of the bigger chapters you guys need to know. In my opinion, one of the harder chapters. Okay, I'm sorry, I'm trying to zoom out just a little bit more. Okay, there we go. All right, so in the following figures, how are hydrogen bonds represented? So an important distinction to make, and I'd like you guys to type in the chat the answer to the question I'm about to say, is are hydrogen bonds full covalent bonds or ionic bonds, or are they intermolecular forces or something like that? Anyone? Ionic? They're not ionic bonds. So hydrogen bonding is, I guess it's kind of ionic actually, hydrogen bonding occurs between covalently bonded structures that are polar. So I'm going to go ahead and draw this out. So the three you want to remember for hydrogen bonding are fluorine, nitrogen, and oxygen. Although in this course, oxygen and nitrogen are the two common ones. We don't talk about fluorine too much. So when you have a nitrogen attached to a hydrogen, as we see with this oxygen and hydrogen, this bond is really polar, okay? So it pulls on the hydrogen, leading to it having a partial positive charge, and this being partially negative. And that's those sigmas is a partial charge, not a full charge. So now when we put another one of these next to it, another nitrogen with a hydrogen, the same thing is happening with this one, with this being partially positive and this being partially negative. So these positive and negative, relatively positive and negative charges interact with each other to form a hydrogen bond, okay? So coming back to this question, the dashed lines between hydrogen and hydrogen, there aren't any. The solid lines between hydrogen and hydrogen, there aren't any. So it comes down to A and B. So are we talking about solid lines or dashed lines? In other words, are we talking about full covalent bonds, or are we talking about intermolecular bonds? Dashed, you're exactly right. So as an example, this is a hydrogen bond, this is a hydrogen bond, and so on and so forth. So the reason I pointed this question out is to talk a bit more about hydrogen bonding in general. So for example, how many hydrogen bonds can a water molecule make? Does anyone know? Should I make this a poll? 4, yeah, someone already nailed it. So the 4 that you don't actually see 4 in this. I was trying to find one that was better, but I couldn't. You see 1, this is 2, 3, and the 4th comes from the other lone pair of the oxygen bond, forming another hydrogen bond with another hydrogen. So that's where the 4 comes from. Yeah, does anyone have any questions about hydrogen bonding? Okay, let you guys type as you need to, and I'm just going to scroll down to the next question. So this one is one of the, in my opinion, not so intuitive parts of biochemistry. This little diagram, even though it's not too difficult, it's just really weird first because we're not used to seeing them. Okay, so the question I asked for this one is, based on the above diagram, which cation is found at the highest concentration in the cell fluid? So I'm going to let you guys answer it, but first I want to go over what we're actually looking at here in the blood plasma. So we see here, and I'm going to look on the right side and the left side of it, is the right side is the cations, the left side is approximately the anions. I don't want to say that it is the anions because there's also some other stuff, but what it's telling us is in the blood plasma, we see magnesium concentration. Oh, I should explain the units, I'm sorry. So milliequivalents per liter, think of that like a concentration. It's a unit of concentration, even if it's not, molarity or anything like that we're used to. And then the x-axis is just a bar graph, so it's just saying what we're looking at. So magnesium is found between 0 and about 5 milliequivalents per liter, about 5, let's say millimolar, just as an example, in the blood plasma. Magnesium, there's my mouse, is found between 5 and, we'll say 10. Oh, I'm sorry, that's calcium. Calcium is found between 5 and maybe 10. Potassium between 10 and 15. And so on and so forth, with sodium being found at a range between like 15 and 165, okay? So the most abundant in the blood plasma is sodium, all right? We're looking at the same thing with anions. Trying to find, there we go. Protein is found between 0 and 20, and so on and so forth. All right, so I'm going to ask you guys a question that shouldn't be tested over, but I think is really important to point out. In all three of these, we see this HCO3 or H2CO3 found in really narrow concentration bands. So it's only found between like 168 and 170 or something like that. Here, a little bit less here, and a little bit more here. Why is the exact concentration of carbonic acid, I should say, so important for that it's so narrow, whereas sodium can range so much, whereas the rest can range a ton, etc. Does anyone know? Okay, I'm not hearing any dings, so I'm going to go ahead and say it. It's the buffer system of our blood. Okay, so this is the thing that makes sure that our blood doesn't get too acidic or too basic. And so it's really important that it have a really solid concentration that's pretty fixed. Okay. The other things I want to point out from this that we can that we can try to use when we're learning is if we're looking at, let's say, I believe bicarbonate, I might have that wrong, right here, no matter what we do, or like no matter where we're looking at, between the cell fluid and anything else, this is at a higher concentration, okay? So what do we know about higher concentrations going to lower concentrations? Passive transport. So the cell fluid wants to transfer some of its bicarbonate away. As it does that, our carbonic acid the equilibrium will shift. Let me go ahead and draw that. Plus and HCO2 minus. So as we lose this bicarb, the reaction moves to the right by Le Chatelier's principle, and so we get more bicarbonate, okay? And that's why this concentration is kept so high, because it needs to be this high, okay? And the same thing happens with the other two, and that's why those bands are so close together. All right, so I'm actually going to go ahead and scroll down, and I'm going to let you guys answer this question now. Based on the above diagram, which cation is found at the highest concentration in the cell fluid? Okay, and let me go ahead and make that poll so you guys can answer it. And our choices were sodium, calcium, magnesium, potassium. And potassium. Okay. Go ahead and vote what you think the answer is based on this diagram. Oh, we already got 3 votes for potassium, 4 votes for potassium. Okay, yeah, it's potassium, exactly right. I'm gonna go ahead and cut it off here. All right, so does that make sense to everyone? Does anyone have any questions about it? I can actually go ahead and zoom in. Okay. All right, yeah, great job, guys. It is potassium, okay? This next question is a little bit conceptual as well. Which of the following explains why pepsin is most effective in the stomach, okay? So this is one of the questions I actually want to turn over and make it into a poll as well. But I just want to let you guys think about it for a second. And I want to explain why this is a question for you guys. So pepsin, or pepsin isn't the most important, but one of the major things that this course does is it asks you to memorize certain protein functions, things like, this enzyme cleaves at this location, etc. And so I want to get you guys into the habit of doing that before you have to, because it can be really helpful. And we've already got 3 people voting for B, 4 for B. Okay, I'm going to go ahead and assume that it's B then. Yes, you guys are absolutely right. And the reason for that is going, one by one. Yes, enzyme activity is dependent on temperature, but it's not really relevant in this case, all right? The stomach is the only place that substrates are found in? Not really. I mean, any protein that's got certain amino acids, which we have all over our body, Finally, it's only active after we eat. Yes, but not because, or that's not why it's only effective in the stomach. But yeah, so it is in fact B. And I want us to think about this. I'm going to scroll down a little bit. So here's the pH of pepsin, or I'm sorry, the enzyme activity by pH of pepsin, I should say. So an important highlight here is it's most efficient somewhere around between 2.5 and 3, I should say. Okay, so I want us to think about how pepsin, cleaves a ton of stuff in our stomach. What does it do around a pH of 7? If we drew this graph out to 7, nothing. Okay, so if our body is naturally somewhere in this range, if our stomach is in any way like punctured or something and gets out, it won't do anything to the rest of our body. And that's a really important thing to keep in mind, that the quality that pepsin has of doing this is also important for our survival. Okay, fumarase is very similar, except based on this graph, where would you guys expect fumarase to be located most at? Would it be in the stomach, just anywhere, floating around the body, etc.? Anyone have any ideas? Okay, got a lot of numbers. Blood, gut. So I would say it's probably in the blood. This one is actually in the mitochondria, which I think is close enough to give it to you guys, just because the pHs are about the same. So yeah, but you're on the right track. That's exactly right. Okay, and finally, lysozyme. I'm not going to waste our time asking the same question. This is its own organelle, and it's slightly more acidic, so that it can break apart these the organelles that are dying, but it's not overly acidic to where it's going to, or it doesn't work in an overly acidic environment simply because you're not going to find those very often. Okay, all right. So now we get into what I personally think is the most challenging and most interesting part of this unit and of this chapter, acids and bases. So I think this is probably everyone's least favorite unit, but I made a couple of questions that I think will really help us look at the versatility of the Henderson-Azerbach equation and the ways that we can use it, the ways that we can solve problems, because I think that's one of the easiest ways that students get confused, and I know that's one of the ways that I struggled a lot as well. So just starting with a couple of conceptual ones and memorization-based ones. When are buffers most effective? I should make a poll for this one too, sorry. Polling. Oops, I think I just canceled it. Sorry about that, guys. Okay, all right, what do you guys think? Where are they most effective? Yeah, you guys are exactly right. And I want to show us, even though I think it's fairly intuitive. And I'm going to do that with the Henderson-Azerbach equation. So this is probably going to be either your favorite or least favorite equation by the end of this chapter. I hope it's your favorite though. pKa plus the log of the conjugate acid over, I'm sorry, the conjugate base over the acid. Okay. So, within plus or minus 1 of our pKa, what does that mean? I lost my mouse. There it is. Okay. It means that if the pKa is 3, then a pH between 4 and 2 will be the effective buffer range. Why is that? Because it makes the difference between the pH and the pKa 1 or -1, and that equals log of acid or base over acid, excuse me, equaling log of base over acid. What ends up happening is when we take this log, we get either 10 or 0.1. Okay, so it means that the ratio of conjugate base to acid is going to equal 1 to 10 or 10 to 1. Okay, why is that important? Because once you get above, 10 times the concentration, your buffer is too dilute in one way or another. So there's too much acid or there's too much base, and it's just not able to do so to resist changes from pH as well, just because there's not enough left of the base or the acid. Okay. Number 5 is fairly similar. Which has a higher pH? 0.1 molar of HCl or 0.1 molar of acetic acid? Okay, so I tried to make this one as easy as I could. Well, not easy, but I tried to make this one, I guess the biggest question is, are these strong acids or weak acids? If you guys want to go ahead and type that in the chat. HCl is strong and acetic acid is weak. Yeah, great job, everyone. So what does that mean for us? And this is, again, another recap just to make sure everyone is okay with this. It means that HCl will completely, so single arrow, dissolve into H plus and Cl minus, whereas acetic acid, which is CH3COOH, oh, I'm sorry, this shouldn't be there, ignore that, will only partly dissolve into CH3COO minus and H plus, okay? So this double arrow tells us this is an equilibrium, meaning that you're never going to have all of the H plus. So when we're looking at pH, we only care about the log of H plus or the log of hydronium, which is about the same thing. And so in both of these cases, we're asking ourselves how many protons are just free in solution. Well, the HCl is going to have more free protons, okay? And that's why it's A. And that's why when you have the same concentration of a strong and weak acid, the strong acid is always more concentrated, okay? Just want to make sure that's okay with everyone. All right, so I'm going to go ahead and zoom in on this just to make it a little bit easier for me to draw because we are going through the math on this question. Okay. All right, there we go. I thought it was B. Did I accidentally circle the wrong one? Oh, yes. Thank you for catching that. I was like, yeah, I definitely got that wrong. So the reasoning behind it being B is because HCl is more acidic, it's got a lower pH. Thank you for calling me on that. I totally forgot. Yeah, so that's the last step of the puzzle. Make sure that you actually are solving for what they're asking for. Very important. Okay, next one. What is the pH of a solution of 0.1 molar acetic acid? So now we're actually going to solve for this, the number that we talked about above. So there's a certain order that we like to go through when we solve these acid-base problems. The first step that I always take is see what I can do with the Henderson-Azerbach equation. Even if it doesn't help, it takes maybe 20 seconds, and if it does end up helping, I don't have to do an ice table, which saves me a lot of time. And if it doesn't, I've only wasted 20 seconds, okay? So using the equation, which I'm gonna write again, just to make sure we're good, pH equals pKa plus log of conjugate base over acid, okay? So right away I see my pKa, they told me, was 4.75. And I know that my pH is what I'm looking for, so I don't know that one. And I know that my total molarity is 0.1. I don't know the individual molarity, or like what I mean by that is how much of it is going to be as acetic acid and how much of it is going to be acetate. But what I can do is I can say that the amount of it that's going to be protonated, we're going to call X, okay? So by definition, if this amount is X, then A minus is going to equal 0.1 minus X, okay? And I think this step right here, we use it a lot in this course, so I just want to make sure, does everyone understand how I did that? If you didn't, please, now is the time to ask. No? Okay, I don't know. I want to explain this because this is I think it's really confusing at first. Once you start using it, it's a lot easier. Okay, so let me draw it up here. So, and I'm just going to use HA for convenience because acetic acid has a long molecular formula. H plus plus A minus. So that's the equilibrium that we see. Okay, so while, and I'm going to go ahead and actually draw the ice table because that'll help. So at the beginning, we start with 0.1 molar. However, we're not looking for the beginning concentration. I'm going to answer your question in just a moment. We're not looking for the beginning concentration. We want the equilibrium concentration. So I'm gonna get to the questions in 1 second. I just want to make sure I explain this topic well, okay? So we start with 0.1 and 0 and 0. So now I know based on what we did in Gen Chem that this is going to be minus x, right? So now I have 0.1 minus x, and x, okay? So I actually did this part backwards, so if we want to ignore this, we totally can, but this is where that comes from. So if I define A minus as x here, then I can rewrite this as log of x over 0.1 minus x, okay? So the reason that I flipped it is because it's effectively the same thing. You just get a different value for x. And the reason for that is your total of HA, so protonated, and A minus, deprotonated, have to be 0.1, right? You only put in that many acetates. So some are going to be protonated, some aren't. But no matter what, they have to add up to 0.1 molar, okay? So if you just label this one as x and this one is 0.1, and if you end up, and I want to, hang on, that's later, sorry, I'm getting ahead of myself. So if we do that, we can save having to draw this ice table to get to here, okay? So now, so sorry, does that make sense how we define one as x and one as the total concentration minus x? Are we all okay with that? Okay, awesome, that's great. So now I want to start getting to the questions you guys asked. So would it be more convenient if we draw the ice table and determine from there, or is it the same? And why would you use the Henderson-Azerbach instead of the ice table? Sure. Okay, so those two questions are effectively asking, do we use Henderson or do we use the ice table? The answer is, depends on the question, obviously. In this case, the Henderson-Azerbach equation doesn't help us enough, right? We have two unknowns, we can't solve it. But how much time did it take us to set up this Henderson-Azerbach equation? 15, 20 seconds, right? And then we realized we were stuck. How much time would it take to set up an ice table and then solve the ice table and all that numerically? A lot longer, especially if we could have used the Henderson-Azerbach. So the first thing that I like to do when I approach these questions, start with the HH equation. If it helps, awesome. I just saved a ton of time, didn't have to do an ice table, super convenient. If it didn't, it's a little bit annoying, but I only wasted 20 or 30 seconds, okay? So does that answer your questions about why we did what we did in the order? Okay, awesome, great. Okay, so now we've realized, okay, we're stuck, we can't use the Henderson-Azerbach equation. So let's go ahead and solve the ice table, okay? So coming back to this where we left off, we're gonna go ahead and say Ka equals H plus, sorry about that, times A minus all over HA. Well, what's Ka? Ka is 10 to the negative that, 10 to the negative 4.75, okay? And I'm just gonna go ahead and, well, I know the answer to this one. It's about 1.8 times 10 to the negative fifth. 1.8 times 10 to the negative fifth. Obviously, we would plug it into our calculator though. Now plugging in the rest of these numbers, we have x for H plus, x for A minus, and then 0.1 minus x here, okay? So now at this point, we also have two ways we can choose to solve this. The small number approximation, or the small x approximation, and the, excuse me, and the quadratic formula, once we solve this all out. I don't want to use the quadratic formula. It's long, it's tedious, I hate it. So I want to try the small number approximation, okay? For the same reason that we tried the Henderson-Azerbach first, the small number approximation, if it works, saves us a ton of time. And if it doesn't, we only wasted like 30 or 40 seconds, okay? So, and I'm going to explain it all just to make sure we're all on the same page on what this small number approximation means, but I apologize if I'm repeating it for you. So the rationale behind this is relative to this 0.1 number, x is tiny, right? So if I were to ask you what's x, or I'm sorry, what's 0.1 minus 0.01? Okay, yeah, that one you're going to say 0.99. But if I asked you what's 0.1 minus 0.000001? In my head, it's basically 0.1, right? Like there's such a tiny difference that we can just go ahead and ignore it, okay? So when we use the small x approximation, we can ignore the bottom x, okay? We can't ignore any of the top ones because they're not being subtracted or added, but we can ignore the bottom one that's going through a subtraction, okay? And I want to tell you guys when we use the small number approximation once I finish this calculation. All right, so now I'm just going to go through and solve this algebraically. So we're going to go ahead and multiply by 0.1. So we're going to get 1.8 times 10 to the negative 6 equals x squared. We take the square root of each. Sorry, that was really pretty. And we get the x equals, I wrote it down over here, about 1.3 times 10 to the negative third times 10 to the negative third. I apologize, I'm still getting used to one, guys. And that's molar. All right, so we used our small x approximation, but we can't just assume that it works, okay? Because what if x is actually a little bit more significant? So we have to check this approximation. How do we do that? We take the concentration we just found, this thing, and we divide it by that initial concentration from what we ignored. So we're going to go ahead and say, okay, so 1.3 times 10 to the negative third divided by 0.1, okay? And then times 100 because we want the percent. We're looking for this number to be less than 5%. Excuse me. In this case, we get 1.3%, which is less than 5%. Great. Check mark. We are done. Okay? All right. So I want to go back and say two things. So first, what if this number was 6 or 7%? Then we have to go back to, and I'm going to try to change colors here. I'm not the best at this. Okay, there we go. So we have to go back to this equation here, and we have to multiply the 0.1 minus x. We're going to have to end up solving a quadratic formula. Yeah, quadratic formula, that's right. So I'm going to go ahead and write it out for you guys over here just so you guys see it. But I'm not going to solve the whole thing because that sounds miserable. Equals x squared. And then this is going to be 1.8 times 10 to the negative 6th minus 1.8 times 10 to the negative 5th x equals that x squared. We would add that to the other side and subtract that. So we would get x squared plus 1.8 times 10 to the negative 5th x minus 1.8 times 10 to the negative 6th equals 0. And then we'd have to use b squared plus or minus the square root. Oh wait, that's not right. God, I haven't used the quadratic formula in months. I apologize. Quadratic. Negative b. I don't know why I said b squared. Let me erase that. There we go. Okay, negative b, and then this is b squared minus 4ac. That's over 2a. Okay? We don't want to do that, so we use the small x approximation first. If it works, awesome. If not, we wasted a tiny bit of time, but now we know we have to use the quadratic formula. Okay? The second thing I want to point out here is when can we use the small x approximation? Technically, we can try it out anytime this number, or sorry, this, I want to change colors again. There we go. Anytime we see something like this, it's worth trying out technically, okay? Because something minus x, well, what if that x is small? However, what that really sells it for me is this part right here, okay? The exponent, I guess the order of magnitude of your k should tell you if it's worth trying. If it's 10 to the negative 5th or lower, so 10 to the negative 6th, 7th, 8th, and so on, it's worth trying out. It probably will work. If it's 10 to the negative 4th, it's one of those gray areas where it might, but if you want to try, excuse me, I'm going to take it. It might work, it might not. It's worth trying out if you want to just go through it really quickly. Worth taking that short time so you don't have to do the quadratic formula. Just don't expect it to work too well, okay? Does anyone have any questions about this whole process, which I know is a lot? Okay, awesome. And if anyone does at any time, again, feel free to just type it in the chat, okay? All right, this next question is very similar. A solution of acetic acid, which it gives us the pKa again, has a pH of 6.75. The ratio of acid to conjugate base is blank, okay? So this is a Henderson-Azerbach equation. I'm going to try to zoom in so I have just a little bit more room break. Actually, why don't I do that? That looks a lot nicer. Okay, there we go. Okay, so again, the first thing I'm going to do for convenience is go to the Henderson-Azerbach equation. So pH, well in this case it's 6.75 equals pKa, so 4.75, plus the log of conjugate base to acid, okay? So in this example, we're looking for the ratio of acid to base. Well, this gives us a ratio. So we don't actually need an ice table. We don't need to do anything. We can work with this. So I'm just going to go ahead and subtract 4.75 over. So I'm going to get 2 equals the log of A minus over HA. Okay. To undo the log, we make the base 10. I don't like the wording, but yes, those cancel out. We get 100 equals A minus over HA. Well, this thing was looking for the ratio, right? So we got 100. Are we done? Is that the right answer? What do you guys think? No, flip it. That's exactly right. Very good observation. So, and I want to, the ratio of acid, oops, oh, stop that. I'm sorry, guys, I'm not, to conjugate base. Okay, so A minus is the conjugate base. Conjugate base. All right, HA is our acid. So to flip this, we're just going to 1 over 100 equals HA over A minus. Okay. So the reason I included this question is to show you guys that the Henderson-Azerbach doesn't just help us get a single number. It's kind of, I mean, I love this formula. I don't want to act biased, but I love it. It's great. But it really helps us with finding ratios. It helps us with solving for a specific value, all that stuff. Okay. Oh God, what did I just do? Sorry. Okay. All right, so these next two problems are going to be a little bit of the stuff that you see more commonly. I just wanted to introduce you guys to some of the ways that we solve these problems before we start. Okay, so the information that I'm, oh, sorry, I see question. Oh, okay, yeah, have a great day. I hope you can see the rest of the live stream. Okay, so a solution containing 50 milliliters of 0.18 molar ammonia with its Kb is titrated with 0.36 molar HCl. So what's going through right now is, sorry, trying to find my mouse, there we go, strong, because we don't have a K, and weak, because they did give us a K, right? Are we all okay with that? Okay, fantastic. All right, so the first part is how much volume needs to be added to reach the equivalence point. Okay, so how do you guys define equivalence point? I think that's one of the ways that we all kind of make mistakes sometimes is, what is the equivalence point? And I made this mistake way too many times. Moles of acid equals moles of base. So yes, you're exactly right. A lot of people say just when it reaches 7. That's not quite true, and this is one of the examples why. So it's when we've added, where's my mouse? There it is. Some number of moles of acid equaling the moles of base. All right, so how do we solve this? We know that moles of acid is equal to molarity of acid times volume of acid. And we know that moles of base is the same thing except with the base, right? So from up here, we got the base has a volume of 50 milliliters. So I'm going to go ahead and write that. And a molarity of 0.1800 molar. And the acid has a molarity of 0.3600 molar and some unknown volume, right? So this is the entire question. It's a fairly easy question, but one that a lot of students mess up on because of the definition of equivalence point. So I'm going to go ahead and solve this. 0.18 times 50 divided by 0.36. So I get the number 25 out of this, okay? So 25, oops, go back. No, I don't like that. Okay, there we go. So I get volume equals 25.00 liters. What do we think about that? Milliliters, yes, saying that. This is one of the other most common mistakes. We don't keep track of our units. So I put liters here because liters are, the SI unit of volume. However, we didn't use liters. We used milliliters here, and then molar and molar. So our molarities cancel, and then this volume has to be in milliliters because this volume was in milliliters. Okay, so this is actually 25.00 milliliters. All right, that's another important thing. So keep track of your units. If I wanted to convert this to liters and write 0.050 liters and do this problem that way, totally fine. Love it. Great job, but be mindful of your units. Okay? All right. And then the second question, what is the pH at the equivalence point? Okay. So in my opinion, this is one of the most tedious questions that they can ask because this is like going back to Gen Chem, unfortunately. And Gen Chem love to make sure that we knew this stuff well. However, it is fair game. It has been asked before. I'm sure it'll be asked again. I don't know if it'll be asked of you guys though. Okay. So the pH at the equivalence point of a strong acid, strong base dilution. Unfortunately, yes. So the pH of strong, 7. When you have a strong and a weak, you have to do 2 steps to get there. The first, and I'm going to try to save room, so I'm going to write this up here. So the first is you have to do the titration. So you have to do acid plus base gets you to whatever. The second is you have to do the equilibrium. Okay. Equilibrium. Okay. All right. So let's go back to this. What is the pH at the equivalence point? All right. So to do the titration, we need to say we have, and this is not an ice table. I want to make sure that's very clear to everyone. Okay. A lot of people will use something similar to get the organization or to make sure they're organized. And I like doing the same thing, but I want to make absolutely certain I say this because a lot of students get confused on it. This is not an ice table. Okay. So we're using moles, not molarity. Okay. So I know that the general equation is HCl plus NH3, and it's a single arrow because of the titration, it's a reaction, not an equilibrium, is going to equal NH4 plus Cl minus plus H2O. Actually, no, that's not right. Ignore that. I think this is just NH4 plus and Cl minus. Yeah, how do I erase? Sorry, I am still learning OneNote. I apologize. Okay. Yeah, let's get rid of that. Okay. And Cl minus. Okay, fantastic. So then I'm going to go back to full screen. All right. So then Cl minus. Okay. So we start out with 0.36 times 25 milliliters. I'm going to go ahead and do that real quick. 25 times 0.36. We start out with 9 millimolar of HCl. I'm sorry, not millimolar, millimoles of HCl. Start out with 9 millimoles of NH3. So when they react, we use all 9 of each of them, and we get plus 9 millimoles, excuse me, and plus 9 millimoles, okay? And millimoles is moles times 10 to the negative third. I'm just doing it for convenience, okay? So then at the end, we have 0 of this, 9 of that, and 9 of that, okay? So the question I always ask is, what do we have left over that contributes to pH? Why does NH3 react completely? So NH3, if you guys remember, at the equivalence point, we've added the same number of moles of acid as we have moles of base, okay? So if we wanted to do the math, we could say 50 milliliters times 0.18 will also give us 9 millimoles. Or we could say, based on the definition of equivalence point, we're going to use them both up completely, okay? Does that make sense? Okay, fantastic. So the question we always ask ourselves once we finish step 1, so once we finish this titration, and I'm going to put a check mark by it, is what contributes to pH here? Well, Cl- is the conjugate to a strong acid, so it doesn't contribute, okay? NH4, on the other hand, is the conjugate acid of a weak base, which makes it acidic, okay? Acidic, okay? So now I want us to pause before we even do any of the math, okay? Your exams, as far as I know, are going to be multiple choice, okay? If NH4 is acidic, I can already tell you the pH is going to be less than 7, okay? So this is one of my favorite ways of making sure I'm doing it right is, does my number make sense? So if I do all this math and I get a, I don't know, 7.4 at the end of it, a red flag should be going up in my head. I screwed up. What did I do wrong? Okay? Make sure that you're checking your work as you go with what makes sense. All right? And does that make sense to everyone? Why that since NH4 is acidic, our number needs to be less than 7? Are we okay with that? Okay. Okay, fantastic. All right. So now let's solve this thing. I'm trying to. Okay, I'm gonna have to scroll to the right. So we know that we have NH4 left, NH4 plus. Let me actually, there we go. And we know that we have 9 times 10 to the negative third moles. But in order to use our ice table or the Henderson-Azerbach equation or whatever we're going to end up using, in this case it's going to be an ice table, we need to go back to molarity. So we need to divide by the volume. Okay. So I know that the volume of my base was 50 milliliters. So should I divide by 50 milliliters here? 75 milliliters. Excellent. Yes, very great for pointing out. This is another of the most common mistakes. This is honestly probably my favorite mistake to make because I make it so often. We have to use the total volume. Okay. Our total volume is exactly like was said, 75 milliliters. Why? It's the volume of our base, 50 milliliters, plus our volume of our acid, 25 milliliters. Okay. So it's 75 milliliters, or 75 times 10 to the negative third liters, okay? And we're going to go ahead and plug those numbers in. 9 divided by 75, and we're going to get 0.12 molar equals 0.12 molar, okay? Does anyone have any questions about how we got here? Okay, awesome. So if we have 0.12 molar, now let's set up our equilibrium, okay? So, okay, here's a great question. So we have a KB, right? So in order to use KB, I need to use NH3 plus H2O. I need more room. NH3 plus H2O in equilibrium with NH4 plus minus. Or I could go ahead and say, I don't really this one, because I think it may. In order to use this equation, though, I need a Ka. Does anyone know how to convert my KB that I have way up there that we're going to have to grab into a KA? All right, equals 1.77 times 10 to the negative fifth. Okay, KW, yeah, exactly right. And more specifically, KW equals KA times KB. Okay, and we know that KW is 10 to the negative 14th, or 1 times 10 to the negative 14th. Doesn't matter, however you memorized it. So let's go ahead and solve that. So ten to the negative 14th divided by 1.77 times 10 to the negative fifth is going to give us 5.65 times 10 to the negative 10th. 5.65 times 10 to the negative 10th. Okay, are we okay with that number? I'm going to assume we are then. All right, we'll go back to, okay. So we've got our KA. So let's go ahead and solve, and set up our ICE table again. Okay, let's scroll back up. Okay. So ICE, I know that I start with 0.12 molar, and these are both 0. And I'm going to pause again. NH3 in these kinds of questions will not always 0. Remember, in this case, we went to the equivalence point. But if we didn't go to the equivalence point, sorry, struggling to find my mouse still. There it is. Then we would need to be cognizant of the fact that this could have a number. If this were 1, we would need to carry that 1 over. If this were 0, we'd carry the 0 over, and so on and so forth. So just be aware of that when you're solving these problems, okay? I don't know why I just did that. There we go. Okay, change is minus x plus x plus x. And then we have 0.12 minus x, x, and x, okay? All right, I guess I'm just gonna work down here, or over here then. Okay, so there it is. Our expression is 5.65 times 10 to the negative 10th equals approximation again for convenience. And of course, I need to check make sure it works, but I'm going to just hope it does for now. So it's 5. I'm going to multiply by 0.12 and then take the square root of that number. Okay, and in the end, I get, where's my mouse? Just had it, there it is. X equals 8.23 times 10 to the negative 6th. And I'm going to check that message in just 1 second. Do you mind to zoom out of it? Yes, I will. I apologize. It's not the most organized, but I definitely will. Okay. Then again, I use the small x approximation, so I have to check that the small x approximation worked. Excuse me. So I'm going to go ahead and do 8.23 times 10 to the negative 6th over 0.12 times 100 to get to a percent. It's going to be tiny, so I know it works, but I'm going to go ahead and just get the number anyways. Times 100. Okay, that's 0.007%. We're good. Okay. So, are we done? I don't hear anything, but the answer is no. We're not done. Why? Because what did the question ask? Again, we have to go back. What is the pH at the equivalence point? We found X, but what is X? So far, it's, going back to this, it's our H plus concentration. So we're really close to done, but we're not quite done. So remembering pH equals negative log of H plus. We're going to go ahead and plug this number in. I'm not going to rewrite it just for the sake of brevity. Yeah, that's a very big problem that we have a lot of times, okay? And the pH ends up being, pH equals 5.0 0.08. Okay? So I know that was a really long problem, so I want to point out one thing before I zoom back out. And that thing is, does this number make sense? Okay, I'm going to keep repeating this for as long as I can while I'm teaching these reviews. We've added, or we have something acidic, so this number is less than 7, so yes, I'm okay with it, okay? Now let's see if I can't zoom us out and show you guys the entire problem. Okay, there we go. We're spoiling a little bit of the next problem, but that's okay. Okay, there we go. And I'm just going to wait on this screen for one moment. If you guys have any questions, feel free. If you guys just want to finish copying this down, go ahead. Sorry about that. Here we go. Where do the millimoles come from? Very good question. So they came from number 8, or like the first part of this problem. That's my mouse. There it is. I went ahead and did 0.3600 molar times the 25 milliliters, 25.00 ml, to get to 9 millimoles. And I did the same thing with the base using the 0.1800 molar times the 50 milliliters. Okay, does that make sense? Okay, awesome. All right. And don't worry, we're almost done. We have, I think, 5 more questions left and about 15 minutes. So I know that this was a really long problem and a really tedious problem, but I just wanted to make sure we're okay with that. Okay, I'm going to go ahead and, actually, does anyone have any questions? Just want to make sure. Okay, I'm going to go ahead and move us on to chapter 3 because we're finally done with chapter 2. So chapter 3, I know that depending on the section that you might have only covered about half of chapter 3, so I tried to keep this one short. Next week we're going to have a lot more problems for it, okay? So I'm going to go ahead and bring it back over here and then zoom this thing in. All right. So chapter 3, what is the second law of thermodynamics? Okay, does anyone know? And you guys can go ahead and type it in the chat. I don't want to make another poll for this. C. Yeah, you guys are exactly right. So the universe tends toward disorder or tends toward entropy. Those are both very good answers. D and B are basically saying the same thing, and then conservation of energy is basically the first law of thermodynamics. Okay. All right. Number 2. So I'm going to go draw this or write this formula out up here. So the formula that we've used in the past is delta G is equal to delta H minus T delta S. Okay. So an important thing to keep in mind here is we want to always know whether delta G is positive or negative, since that tells us spontaneity. Okay. And so that's the reason this table is, in my opinion, a really important thing to at least understand, even if you don't memorize it, which you don't have to, just so you're always kind of aware that how these things affect it. Okay, so if we have a positive delta H, then our first term is big and positive, right? And then we're subtracting minus a positive delta S, and temperature is always positive because it's in Kelvin. So we're subtracting another big positive thing, right? Thing. In other words, the numbers themselves are going to be the big question here. If you have a really big H, then it might be positive. If you have a really big S, it might be positive. But for these, we like to say it's temperature dependent. Because the delta H and the delta S are pretty much constants for a reaction, right? You're always going to use this amount of each reactant, therefore you're always going to have this amount of energy change and so on. So it's temperature dependent. So is delta G, we'll say positive at a high or a low temperature? Does anyone know? at a low temperature. You guys are exactly right. So I'm going to go ahead and say positive at low temperature. Okay. All right, next question. Or next line in the table, sorry. All right, again, we have a big positive number. And we're subtracting a big negative number. All right, and the reason the sign of this thing is negative, and again, p is always positive. Positive times a negative gives us negative. So what's a positive number minus a negative number? It's always going to be positive. You're exactly right. Always positive. Okay? All right, now over here. A big negative number minus a big positive. What do you guys think? A negative minus a positive? This is going to be even more negative, right? So this is always negative. Okay? And finally, this last one, a big negative number minus another negative number. Again, just like the positive case, this one depends on the temperature. Okay, so temperature dependent. And I'm going to go ahead and skip asking you guys high or low temperatures. It's just the opposite. So it's going to be positive at high temperatures. And the reason for that is because at a high temperature, it's more entropy driven, if that's how you want to think of it. Or in other words, delta S plays a bigger role. Minus a negative is just like adding a positive. So as temperature increases, the significance of delta S increases, and eventually delta G will become positive because of that. Does anyone have any questions about this table? Okay. All right. Which of these describes a favorable reaction? So now we're actually going to use delta G. What do you guys think? Does anyone know? Ooh, we got a lot of dinging. B, yes, everyone is exactly right. A negative delta G is a spontaneous or a favorable reaction. So I'm going to go ahead and come back up here. So this is never spontaneous. This is always spontaneous. Spontaneous. Okay, this is spontaneous at a low temperature because it's positive at a high. And this is spontaneous at a high temperature. All right, does that make sense to everyone? Okay. All right, and actually we're pretty much done because these last two are just conceptual questions. So for which K does delta G indicate a favorable reaction? Okay. I see a question mark. So K, the equilibrium constant. Sorry, I should clarify. So I see a question mark, so I'm going to go ahead and just go through this one real quick. The equation that we're looking at is delta G is equal to RT ln K, ln being natural log. Okay, so temperature is temperature in Kelvin, excuse me. R is our ideal gas constant, which which is positive. Okay, so these guys are always positive, which means that the natural log of K and the negative sign are what determine delta G. Okay, so remember, favorable reaction means we want a negative delta G, meaning that since this negative right here exists, we want this number in the natural log of K to be positive. Okay, does that make sense to everyone? I'm going to go ahead and repeat it because I think I said a lot of positives and negatives. R and T are always positive. Two positive numbers multiplied together, positive number. Okay? To be a favorable spontaneous reaction, we want delta G to be negative. Okay? Because there's a negative sign on the right side of the equation, we want natural log of K to be positive so that the entire term is negative to make delta G negative. So under what conditions is ln of K positive? Okay, so I guess I'll give you guys, oh, here we go. A. Yes, you guys are exactly right. When natural log of k equals 0, when k equals 1. When k is above 1, the natural log is positive. When k is below 1, the natural log is negative. So you guys are exactly right. So number 4 and number 2 were just designed to make sure that you guys see these equations. Oh, oops, no, I don't want that. And know like how they affect things, okay? And our last question is rank the states of matter by entropy. So the highest entropy is first, okay? Oh, we have D. Yeah, you guys are really fast. You're exactly right. And this is another conceptual question to make sure we understand that entropy is disorder. Gases are free to move wherever they want, so they're really disordered. Liquids are bunched together, or like they're stuck together, but they move around a lot. Solids don't move around anywhere near as much. They kind of vibrate together, okay? And that is today's review. So I'm going to go ahead and, give you guys 2 or 3 more minutes to ask questions and then stop recording. And then if you want to ask more questions afterwards, feel free. But yeah, how would you say to best prepare for the exam? So in my experience, and I don't want to, okay. And I don't want to say that this is going to be the case this semester since no one knows how the online setting is going to affect things. But the problem sets, in my experience, were always more difficult than the exams, okay? They covered the same formulas, the same ideas, the same concepts as the exams, but they were just a lot harder. So if you can do the problem set, and I haven't seen your problem set, so that might not be the case here, but I think it is. So if you can do the problem set and understand how to do the problem set, feel good about yourself. Like that's a really good accomplishment. That's a really big accomplishment. And just study a lot of the topics on there. If your professor posts practice exams, use the practice exams. Make sure you understand everything in the PowerPoints really well. Consult the book if something in the PowerPoint is not clear, stuff like that. But in general, the problem sets are going to tell you the most important things on the exam. The others will be there. Practice exams your professor posts are going to be the most accurate you can use. And then just understanding the slides next, okay? Our exam 1 questions more conceptual calculations. It's a mix of both, but I would say, and again, not sure how online changes things, but because there's a time limit on exams, usually they don't like to throw in a ton of math questions, excuse me, especially if they're like number 9 on chapter 2, because this will take you guys like 15 minutes. And so they really don't want to throw you guys like these really complex questions. They just want to make sure you understand the topics. So expect some of each, but primarily conceptual. The questions that I made, I don't think they're indicative of exam questions simply because I didn't want them to be. Our weekly reviews are mostly to make sure you guys understand the content well and are able to like apply the content. So I just want to make sure you guys have that foundation so that you can solve your problem sets, so that you can solve your exams. I would say that the most indicative are probably stuff like, I'm trying to think, number 5 on chapter 3 is probably a common exam question. Some of these questions are fairly common, stuff like number 4, number 3. I could see number 2, it's been on exams before. Number 1, maybe not. Stuff like these, number 3 and number 2 of chapter 1, are possible, but they're not entirely common. So that I wanted to throw them in there just to make sure you guys saw them. They're not always there. So it really depends on your professor. It depends on how things being virtual changes things like that, okay? Okay, all right. I'm gonna go ahead and stop recording this.